In this video, we'll talk about measuring the magnitude and phase differences between two sinusoidal signals. Steady-state response problems nearly always boil down to determining the magnitude and phase differences between sinusoidal signals, so it's important to understand these concepts in physical terms, rather than simply as mathematical relationships. First, let's briefly review the basics of what we mean by a system's steady-state sinusoidal response. If we apply a sinusoidal signal to a circuit, eventually all the voltages and the currents in the circuit will also be sinusoidal signals with the same frequency as the input. For example, let's apply a signal with some frequency omega and amplitude A and phase angle theta to a linear circuit. Eventually, every other signal in the circuit will be a sinusoid with that same frequency, but possibly with some different amplitude, say B, and a different phase angle, phi. The relationship between our input and output at some frequency can be expressed as a gain and a phase difference. These parameters can be used to characterize the behavior of the circuit at that frequency. Gain is defined as the ratio of the magnitude of the output sinusoid to the magnitude of the input sinusoid. The phase difference is defined as the phase of the output sinusoid minus the phase of the input sinusoid. The choice of input and output is somewhat arbitrary. Gain and phase calculations are dependent upon that choice of input and output. Let's take a look at using sinusoidal input and output signals to determine the gain. Suppose that the two signals we're interested in look like this. U of t is the signal we're considering to be our input, and y of t is the signal we've chosen as our output. The amplitude of the input sinusoid is delta u, and the amplitude of the output sinusoid is delta y. To calculate the gain between the input and the output, we simply take the ratio of the output amplitude to the input amplitude. Now let's take a look at using measured response data to determine the phase difference between two signals. It's important to notice that when determining the phase difference between two signals, the individual phases of the two signals aren't important. To determine the phase difference between two signals, we just need to measure the time delay, delta t, between the two signals. This time delay is the time between 2 points with the same phase on the two signals. For this example, I've chosen 2 points that correspond to the minimum value of the signals. We can calculate the phase difference from this time delay by comparing it to the period of both of the signals. Since the time period of a sinusoid corresponds to 360 degrees, or 2 pi radians of phase difference, we can calculate the phase difference corresponding to this time delay by taking the ratio of the time delay to the total period and multiplying that by 360 degrees. Next, we'll apply these concepts to the measurement of impedance. The impedance of a circuit is defined as the ratio of a voltage phasor to a current phasor. In polar coordinates, the impedance is defined by its magnitude and phase. The magnitude of the impedance is the magnitude of the voltage phasor divided by the magnitude of the current phasor. The phase of the impedance is the difference between the voltage phase and the current phase. These are the same calculations we were performing for an arbitrary definition of inputs and outputs. If we consider the current to be our input and the voltage to be our output, the process of measuring impedance is the same as the process of determining the gain and phase difference between an input and an output. So if this is a voltage sinusoid and this is the corresponding current, the impedance magnitude is just the ratio of the magnitude of the voltage to the magnitude of the current. Similarly, if the time delay between the two is delta t and the period of both waveforms is capital T, the impedance phase is delta t over capital T times 360 degrees. As an example of impedance measurement, we'll measure several different impedances in this RC circuit. To do this, we'll apply a sinusoidal voltage input across these terminals. We'll determine the current, I of t, by measuring the resistor voltage and dividing that by the resistance value. This current will be the current through all of the circuit elements. The resistor impedance will be the resistor voltage phasor divided by this current phasor. The capacitor impedance will be the capacitor voltage phasor divided by this current phasor. And the overall impedance of the series combination of the resistor and the capacitor will be the voltage phasor corresponding to Vn divided by this current phasor. To see the effect of frequency changes on the impedances in the circuit, we'll apply sinusoidal voltages with low, medium, and high frequencies. Omega sub c, also known as the cutoff frequency, equals 1 over the product of the resistance and the capacitance. We'll use omega sub c over 10 as our low frequency, omega sub c as our medium frequency, and 10 times omega sub c as our high frequency. One important thing to keep in mind is the units of frequency. Omega sub c, as defined here, has units of radians per second. Use those units in any calculations you perform. However, most lab equipment works in units of hertz, or cycles per second for frequency. Since there are 2 pi radians in one cycle, you need to divide the frequency in radians per second by 2 pi to get frequency in hertz. So if the results you're measuring don't match up with your calculations, first make sure that your frequency units are consistent between your measurements and your calculations. This is my circuit. My resistor is here, my capacitor is here. I'm using channel 1 of the waveform generator, the yellow wire, to provide power to the circuit, and this terminal of the capacitor is grounded. Using channel 1 of the oscilloscope, the orange wire and the orange wire with a white stripe to measure the voltage across the resistor. Using channel 2, the blue wire and the blue wire with a white stripe to measure the voltage across the capacitor. The current through all of the elements will be determined using a math channel to divide the resistor voltage by the resistance, which in my circuit is 100 ohms. Now let's apply power to the circuit and measure the parameters we need to determine the resistor and capacitor impedances at a particular frequency. I'm applying a sinusoidal input, and I've chosen arbitrarily a 2 kilohertz input frequency. This is a random choice. You'll have to determine the correct cutoff frequency and apply the appropriate frequency input when you do the lab. The amplitude is 2 volts. Let's go to the scope and look at our signals. I've already set up my scales on channel 1 and channel 2, and I've added a math channel, which is C1 over 100, which is the current through the resistor. I can measure some of the values automatically by setting up a measurements window. Click on View and select Measurements. To add a measurement, click on the Add button. All of the measurements I'm going to add are predefined. I want an amplitude for channel 1. That's under the vertical scale. So let's pick a maximum value. Add that. I'll also want the maximum value of channel 2. I'll add that. And I'll want a maximum value for the math channel. I'll also need the period of the signals. I'll use channel 1 and measure a period. So now I'm showing the maximum values for channel 1, maximum value for channel 2, and the period, and the maximum value for the math channel. This column over here will give me the values that I need for my calculations. Now I just need a measurement of the time shift. I'll typically use X cursors to find that. I don't really need to determine the time shift between channel 1 and the math channel. There's no time shift associated with a resistor, so those are completely in phase. For the capacitor, I'll grab an X cursor, choose the maximum value on the capacitor voltage, which is the blue line, and I'll choose the maximum value on the current, which is the red line. This gives me the time delay between the two. Notice that the capacitor current leads the voltages. Finally, let's get our measurements to determine the impedance of the resistor-capacitor combination. I'll leave C1 in place to measure the current, but now I'll use channel 2 to measure the voltage across the entire RC combination. Now on the scope, channel 2, the blue line is the voltage across the entire series combination of the resistor and the capacitor, and the red line is still the current through that series combination. Lab equipment nearly always displays sinusoidal frequencies in hertz, or cycles per second. Calculations are done in radians per second. Make sure that you use consistent units when comparing measurements and calculations.